Hello friends, today we are going to discuss a very important topic of network analysis, which is charge. It is important topic because any energy transfer which is accomplished in electrical circuits is due to the transfer of charge. We know that charge flows from a point of higher concentration to a point of lower concentration. At a point the concentration is high and at some point the concentration is low. The charge always flow from a point of higher concentration to point of lower concentration. It is concentration. So even if it is negative charge, the negative charge will flow from point of higher concentration to a point of lower concentration. Friends, in our school days we have seen that when we rub a piece of scale with our hairs, then whenever some pieces of paper comes in proximity with this scale, they start to dance. So we know that some transfer of electrons happens from our hairs to the scale, due to which the scale acquires positive charge sometimes or maybe negative charge. It depends on the material of the scale, whether the electrons transfer takes place from scale to hairs or from hair to scales. So the concept of charge is not new to us. We are not new to this concept, but now in our electrical circuits we have to extend our knowledge about the charge, and we'll go further that we learn some new things about charge. Charge is represented by Q and unit of charge is coulombs. Unit of charge is coulombs in MKS system. Also on one electron, if we consider one electron, the charge on one electron is 1.6021 into 10 to the power minus 19, and the unit is again coulomb. Now what is the relation between charge and current? Current, which is given in amperes, is the rate of change of current, rate of change of charge per unit time. This is the important relation between current and charge, that current is rate of change of charge per unit time. From here we move ahead to a very important problem which is many times asked in competitive examinations, that if 1 ampere current is flowing from a particular cross section for 1 second, then how many electrons will pass from this particular cross section of this wire? We will solve this question now. From the formula we have that I, which is current, is equal to rate of change of charge per unit time. Now in our case it is given that current is 1 ampere. We have to find out the charge, how much charge has to flow, and now time has been given as 1 second. Now this charge which has to flow comes out to be 1 coulomb charge has to flow. If 1 coulomb charge flows for 1 second, then it becomes 1 ampere current. The problem is how many electrons have to flow. Now charge on one electron is 1.6021 into 10 to the power minus 19 coulomb. So if we have to calculate number of electrons in 1 coulomb, then we can easily find out that if one electron is having this much charge, then 1 coulomb will have this many electrons, 1.1 upon 1.6021 into 10 to the power minus 19 electrons. This many electrons will come in 1 coulomb of charge, and the value will come out to be 6.24 into 10 to the power 18 electrons. So this is a very important number. 1 coulomb of charge is 6.24 into 10 to the power 18 electrons. Also, if 6.24 into 10 to the power 18 electrons are flowing for 1 second from a particular cross section area, then the current will be 1 ampere. If this is a wire at this cross section area and here electrons are flowing, then 6.24 into 10 to the power 18 electrons have to pass through this cross section area in 1 second, and then 6.24 into 10 to the power 18 electrons have to pass this cross section in 1 second, and then we will call it a flow of 1 ampere current. This is a very important deduction. Now next we will learn about the potential. Work done per unit charge is potential. If work done per unit charge is potential. Now certain amount of work is done on certain amount of charge, then there will be a certain change in the potential level. Okay, and also from definition we know that power is equal to voltage into current. P is equal to V into I. This is a very familiar equation. Here also we can write that W is work done. Now Q is charge and V is voltage. So from here we can write that rate of change of work done per unit charge and current is rate of change of charge per unit time, and this is power. This dq cancels out from here and power becomes rate of change in energy per unit time. Energy and work done are similar, so this is power. Power is rate of change of energy per unit time. Further, we move ahead to find the force acting between two charges kept at a distance of r meters. If the value of this charge is q1 and this charge is q2 and they are r meters apart, then the force acting between these two charges can be given by q1 q2 upon 4 pi epsilon r square. So it is inversely proportional to the distance. If distance is more, then the force will be less, and if distance is less, the force exerted on other charges will be more. Here q1 and q2 are in coulombs, epsilon is the permittivity, r is in meters. For free space, the value of permittivity is 8.854 into 10 to the power minus 12. This is the value of permittivity for free space and the unit is in farads per meter. So now let us look at one example. If 3 amperes current flows for 3 seconds through a conductor, what amount of charge in coulombs passes through a particular cross section in this conductor? Again, you can read this question. The question is very simple and we can use this simple formula for this. I is equal to dq upon dt. I is given as 3 amperes. Here we need to find out charge in 3 seconds. So here the charge comes out to be 9 coulombs. 9 coulomb charge flows through one cross section if 3 ampere current is flowing for 3 seconds. Next, one more example we can see that how much work done or energy is required for moving a column of charge from 12 volts to 14 volts. So from today's session we know that voltage is equal to work done or energy per unit charge. Now the voltage difference here is 14 minus 12. We need to raise the voltage by 2 volts. How much work done will be required in joules? This will be in joules upon the charge is given as 1 coulomb. Here it is written that a column of charge, that's why we can take here 1 coulomb. So here 2 joules is the simple answer to this question. These were the important points which we planned to discuss in this session. Further, we will keep on discussing important concepts of electrical circuits in the upcoming session. For that, you have to subscribe our channel. Please subscribe Technitude. Thank you. Thanks a lot.